Okay, welcome. This video is going to be discussing one of the last sections in the chapter 18, so talking about acids and bases. This section is about solvent leveling. In this section, this should be fairly brief. In this section, talking about solvent leveling, we have a simple statement, is that the strongest acid or base, and this is the important part, in water is H3O plus and OH minus. So hydronium hydroxide. So let's underline this again. This is important. The strongest acid or base in water is hydronium or hydroxide. So for an example, let's just look at three strong acids. So we have HCl, HBr, and HI. And what we looked at one of our other videos was the relative strengths of all of these, and we said that, well, they're all strong acids, so they're all the same strength. They're all strong. They all dissociate completely in water, so we can draw reaction arrows that show them completely dissociating. And let's look again at the conjugate base of each of these. So they all produce hydronium. And it's not chloride, it is bromide. And iodide. So this idea of solvent leveling is that since the strongest acid or base in water is H3O plus or hydroxide, if we add any acid that's stronger than water, it's going to protonate water and make hydronium. So adding more acid, adding more strong acid, just produces more hydronium. And the same thing would apply with a base. Let's look at a strong base really quickly. Let's go back actually and label these. We know these are acids. These are our strong acid. That means water is acting as a base. This is the conjugate acid, and this would be the conjugate base. If we were to look at a strong base in water, we know hydroxide's a good strong base, but just to be clear on the difference here, that hydroxide is the strongest base that can exist in water. Anything stronger than that is going to make more hydroxide. Let's look at the oxide ion. So that is O2 minus. It's got 4 lone pairs of electrons, so just a oxygen with a 2 minus charge. If we add that into water, where would oxide come from? Great question, glad you asked. Oxide could come from something such as potassium oxide, so K2O. That's one good example. Magnesium oxide or calcium oxide are both sources of oxide. Potassium oxide is going to be soluble in water. Magnesium and calcium oxide are sparingly soluble, so they'll only make a little bit of oxide. This is going to accept a proton from water, so that makes it the base, and water is going to donate a proton, so it's the acid in this case. And again, this is strong, so it goes completely, and what we end up getting is 2 moles of hydroxide. So the oxide takes a proton from water, and that leaves both of them with 1 proton, so we have 2 moles of hydroxide. So again, as you can see, adding anything stronger than water just produces more hydronium or hydroxide. So if I wanted to know of these 3 acids we discussed earlier, hydrochloric, hydrobromic, or hydroiodic, which one of those is the stronger acid? We've kind of talked about this in the strengths of acid video, and what we have to look for to see the relative strengths of these is we have to look at their conjugate base. And in order to kind of judge this, if they all dissociate completely in water, we would have to use a different solvent in order to see their extent of dissociation, to see which one's going to be the stronger one. Remember, the one that dissociates more is going to be the stronger acid, since they all dissociate completely in water. In water, they're all equal, or what we say is that water has leveled them all to the same strength. So that's where this solvent leveling comes in. So water's acting as the solvent, and it's leveling all of them to be the same strength. So if we switch to a different solvent, then we can actually start to see their acid-base strength. So we switch to a solvent. And in this case, since we want to measure the acid strength of our three strong acids here, we're going to switch to a solvent that is a weaker base than water. In this case, if we want to find a weak base, we should just use a weak acid because the conjugate base of a weak acid is a weak base. So we're just, for simplicity, keep everything the same. We're going to switch to acetic acid, CH3COOH. Another way of abbreviating this, just for future reference, is ACOH, where we know that OH group is going to be the proton donor, and AC stands for acetic, so this would represent acetic acid. So if I redraw this acid-base example we had up here, but with acetic acid as the solvent instead of the water, we have HCl plus CH3COOH, HBr plus our acetic acid, and HI. Now our acids still act as acids, so we can just label those as the acid. And now acetic acid is going to act as a base. Now this is a little bit strange because we just called it an acid, but it's an acid and water, and remember this is acetic acid is a weak acid compared to our hydrohalic acids like HCl, HBr, and HI. So in this case, the stronger acid prevails and makes the weak acid into a base. Now these are no longer strong in this case. We switch the solvent, so now we're leveling them to a different strength. And what we can see now is we end up with this equilibrium where they're going to dissolve or dissociate to different amounts. And we end up with chloride, bromide, and iodide. Those are giving up the proton, so they're donating a proton, so that's the acid component. And now this is kind of the weird part where acetic acid has to accept a proton as a base, and so this becomes CH3COOH2 with a positive charge. And this happens in all three cases. Now again, we look and compare to see which of these three is going to be the stronger acid. We would have to look and compare their conjugate base and acid. So let's just label these. This is the conjugate base, and this is the conjugate acid, because this could redonate a proton back in the reverse direction. Now in this case, the conjugate acid is all the same. It's all of this protonated acetic acid. And so what we really need to look for is the difference in the three conjugate bases. And one thing that we kind of looked for in this case was we looked for which one is the most stable, which one is happiest with that negative charge. That's going to be able to carry that negative charge, and it means that's the acid is going to dissociate more in that direction. So if we just look really quickly, I- is a very large ion. So that means it can spread that negative charge over a large area. This stabilizes the molecule, makes it happy, so it's more stable. Which means that the more stable the conjugate base is, the stronger the acid. So in this case, if we could list a Ka value or a K value for these three cases, we could say that the equilibrium constant for Hi would be greater than the equilibrium constant for HBr, which would still be greater than the equilibrium constant for HCl. So even though in water all three of those are strong acids, in a different solvent, when we switch to a different solvent to get away from this solvent leveling problem, we would see that Hi is in fact the strongest acid out of those three strong acids. So even though we call all three of them the same, they're not. They have different strengths.